Hello and welcome to Laser Lounge. This is our second series in our interactive webinar edition called Laser Lounge. And we've devised this Laser Lounge to keep in touch with you, our customers. Today we have a product introduction. I'm Elizabeth Illy, Head of Marketing from HÜBNER Photonics.
And I'm Elena Vasilieva, a Product Manager for Cobolt Pulse Lasers.
So a little bit about Laser Lounge. Basically, bring a cup of coffee, take a half an hour, come and listen to some of our laser experts, introduce their products, have a live demonstration, and basically have a talk with us because we love to talk lasers. Especially now, of course, in the Corona times, we haven't been able to interact with you, our customers, at either exhibitions or in our regular face-to-face meetings. So we've been exploring our digital alternatives, and we came up with Laser Lounge. So basically, I mean, the topics will range from anything from new product introductions and live demonstrations like we have today, through to user forums where you can share experience amongst yourselves of your experience of the Cobolt lasers. So keep an eye out for our future editions. And today, Elena, what are we going to talk about today?
So we will start with the first introduction about Tor XE, our new product, and then we will have our product engineer, Charlotte. Hey, Charlotte, are you there?
Of course, I am here.
Hi. So we will have a live session in the lab with Charlotte, and then afterwards we'll finish off with some questions.
Sounds great. All right, while Eleanor is miking up, let's go through a little bit of the housekeeping rules. So if you want to increase the size of the video or decrease or increase the size of the presentation, just move that horizontal bar, hover over it and move it up and down. Feel free to drop any questions in during the whole session. And you do that on the right-hand side in your dashboard there under chat. And then at the end of the session, as Eleanor mentioned, we'll answer the questions. Also, if you want to go into full screen, that's the obvious big square on the top right-hand side. So, okay, I hope you enjoy it. Eleanor, over to you.
Yes. So, hi again, I'm Elena and I'm Product Manager for our Tor series. And today we will talk about our new product, Tor XE. And Tor XE belongs to the family of Tor lasers. So we have 3 lasers in the family, Tor XS, Tor, and Tor XE. So the name of Tor XS stands for its small size. So it's a compact Q-switch laser. It's available at 1064 and 532 nanometers with in energy in infrared up to 100 microjoules. And the repetition rate can be changed from a single pulse up to 1 kilohertz. So Tor lasers are available at 3 wavelengths, 1064, 532, and 355, with an energy up to 150 microjoules for infrared. And the repetition rate is fixed at 7 kilohertz. So our Tor XE is currently available at 1064 nanometers with an energy 500 microjoules, and the repetition rate of the laser can be changed from a single pulse up to 1 kilohertz. So basically, if we look at Tor XS and Tor XE, they are quite similar in a way that they are triggerable lasers. So one needs a trigger to operate them, either external or internal, and Tor is a free running laser. So let's look closely to the specification of Tor XE. So as I mentioned, currently it's available in infrared, so 1064, and it has a nanosecond pulses. And here we have a picture from oscilloscope where one can see that the duration of the optical pulse is about 2.5 nanoseconds. So the energy is 500 microjoules and the beam quality is great for the pulse laser. Its m-square value is less than 1.3, and one can see the picture of the laser beam here. So the special cavity design of our lasers differentiate them from a typical passively Q-switch lasers, and the difference is that because we have a traveling wave, we actually don't have any spatial hole burning. So that provides us with an excellent jitter less than 2 microseconds and the power stability less than 3%. So the operation of the laser is set by a trigger signal, and it can be either a single pulse or anywhere between a single pulse and 1000 Hertz. So the trigger modes, there are 3 trigger modes available. We have internal, external, and gated trigger modes. And we'll talk a little bit more about them just a minute from now. So the pulse parameters, that is quite an interesting feature. The pulse parameters are the same regardless which operation frequency you choose. So the size is compact and the electronics is integrated inside the laser head. And one more nice feature is that the laser head has internal pulse monitor. So you can actually monitor the repetition rate the laser is running at. One can communicate with the laser either using USB port or RS-232 or actually both, and that is very handy. For example, if you are sending commands using RS-232 communication port, but at the same time you can open our software and look at the parameters of the laser and the repetition rate you are running the laser at. The software is available on our webpage. It's free for download, so please check it out. Oh, I forgot to mention, here is the picture from oscilloscope of our jitter, and as you can see, it's less than 2 microseconds. But Charlotte will tell us more and actually show how we measure this parameter. So when you download our software and get it running, this is what you will see. This is the Cobolt Monitor software, and you can choose here the parameters or the trigger source. It's either internal, external, or gated. So you can turn the laser on and off using these 2 buttons, and you can see that interlock is shining green, so you're good to go. So once you press this more button, you will end up with extended view here, and you can set up your frequency here if you're using the internal trigger signal, and you can monitor your repetition rate right next to it. So let's talk a little bit more about the differences between the trigger modes. So as I mentioned, we have internal trigger modes. That means that electronics is driving the laser at the frequency that you set in the software. And you can monitor the frequency that is measured by the laser here, either in software or using this SMB connector on the back of the laser head. This SMB connector can also give the signal that can be used for synchronization with your other equipment. So and now we move towards the external trigger mode. So the external trigger mode, one needs an external source to trigger the laser, but we have a lot of flexibility on the duration of the external trigger. So it can be anywhere between 1 to 200 microseconds, and the laser will be triggered on the rising edge of your external trigger. You can monitor the repetition rate the laser is running at in the Cobolt Monitor software here. And to apply the external trigger signal, you can either use this port that is called control, it's a Molex connector, or you can use SMB connector on the back of the laser head. So gated trigger mode is quite interesting because it's a combination of both internal and external triggers. So basically, if we look at the time diagram, so when your external signal is on, the laser is shining at the repetition rate that was set in the Cobolt Monitor software. And again, you can monitor the repetition rate the laser is measuring here in the software right next to it. So the demand on the external trigger signal is that it has to be longer than 200 microseconds, and that's basically it. So as long as your external trigger is on, the laser is sort of operating in a similar to the burst mode of our Tor laser. And with that, I'd like to give a word to Charlotte, who will show us how the laser is actually working in the lab. So Charlotte, are you here with us?
Indeed, I am here with you. Thank you for a nice presentation, Elena.
My pleasure.
Then Did. Hey everyone, my name is Charlotte. I'm the product engineer of of our pulse lasers, and I'm here today to show you our latest addition to the family, the Cobolt Tor XE. So we're actually gonna look a little bit at how the different trigger modes works in the lab and pulse parameters and so on, which might be interesting to see. So I actually have the one laser here with me in my hand, and you can see, despite the 0.5 microjoule of energy and quite powerful, it fits nicely in the palm of my hand. So if we look at the front of the laser, we have the aperture where the beam comes out. We have if I angle that so you see a little bit better, we have a shutter to open and close it. If we look at the back, we have a Molex connector, which you can use for a variety of purposes, the key box for CDRH, applying the trigger signal, RS-232 communication, so on. We have the power supply connector, we have USB for connection. You can apply your external trigger signal on the SMB connector, and we also have an SMB to monitor the signal coming out from the laser. So, and I, of course, have it all set up here in the lab. So I have my Cobolt Tor XE. It's been sitting here. It's waiting for you to have a look at the demonstration. I have mounted it on a temperature-controlled plate to make sure that it doesn't overheat. So it needs a little bit of temperature control to function properly. To it, I have connected my function generator to be able to provide a variety of trigger signals, so we can play around a little bit with that. To monitor the pulses, which is what's really interesting here, and see what happens when we run different trigger signals. I have my photodiode, and all these three, including the signal out, I have connected to my oscilloscope that I will show on my screen. So let me share. And before I share my screen with you, we need to point out that this is a class 4 level laser, meaning it can really hurt your eyes, or your colleagues' eyes. So be sure that you have the laser beam well contained. As you see, I have no beam here, and that you protect your eyes. So let's put our goggles on. So I will share my screen with you before we get started. And of course, it's a little bit of clicking around. You will be with me in a second. So there we go. And I'm gonna move this window so I see what I'm doing. There we go. Now to your right, you have the Cobolt Monitor software, which is the software that accompanies the laser. As you can see, the laser is on with the power on, and obviously it's connected to the monitor. The safety interlock is connected on my Cobolt monitor key box. So we have the safety interlock, we have some LEDs, and you can actually connect your RS-232 on the back. On the mode settings, as Elena told you, you can choose your trigger signal, and in the message box, the laser will tell you how it is feeling. So if it's on, in this case, we have the auto start completed, meaning it's on, or if it has an error. On the left side of my screen, you actually see my oscilloscope live in the lab. So if we open the shutter here, you will see we have the laser pulse coming in and being detected by my photodiode. And if I put my card, you should be able to see the beam. Then of course it disappears. So if we click more, we get a little bit more information about the laser. And we have some temperature stabilizing elements. As long as you don't have a fault and they're shining green more or less all the time, you're good to go. You don't need to worry. What's interesting for the Cobolt Tor XE is this box, which helps you to operate your laser, where you can select your trigger source. And of course, we have the monitoring of the repetition rate and the laser current. And when we send you the laser, it will be set into the internal triggering setting, meaning that the integrated electronics, it's all integrated into the laser head, will provide the laser with everything it needs to just get going. All you need to do is put it on a heatsink, connect your power supply, and the laser will start up. Looking at the pulse we have coming from the laser now, as you see here in on my oscilloscope, the pulse is about 2.2 nanoseconds long, and it is measured now so that we're sampling over some hundreds of pulses overlapping to so that we can see also how the stability of the pulse looks, and we can see that I have put some cursor here to illustrate what would be a peak to peak of roughly 10% variation, and as you can see, we're well below that. So this laser runs in, very smoothly in this way. Being in internal trigger mode, you can actually change in the software. You can change your repetition rate. That's a little bit too much. So something like that. And we can actually see how the laser changes the repetition rate. We go back and forth. If we now instead change to the external trigger signal, which might be more interesting if you're synchronizing the laser to other equipment, we click external. Upon changing the trigger signal, the laser will very quickly restart itself, but as you saw on the oscilloscope, pretty much nothing happens. I'm going to change view here. So, recall. There we go. So now instead we are looking at my applied trigger signal, which is supposed to be purple, but I can see that it's a little bit saturated, so please bear with me. So it's a square signal. I know by heart that it's 300 microseconds long in this case. We have the blue signal, which is our optical signal, so we see the pulse as a very short peak here since it's a nanosecond pulse. And now if I actually change the length of my trigger signal, absolutely nothing happens, which is quite convenient. So what happens when you trigger it in the external mode is that the laser will trigger one pulse for each rising edge, meaning that you have quite a flexibility in how you design your trigger signal. As long as you have a rising edge, the laser will generate one pulse per rising edge, from single pulses up to 1 kilohertz. When we do this, we can also look at the, what we call the triggered pulse jitter, meaning that we'll trigger the oscilloscope to sample the optical pulses starting from this rising edge. So if we change our oscilloscope, sneak in here, look, there we go. So what we see here is an assembly of pulses collecting, and the oscilloscope will measure the time between the earliest pulse and the latest pulse, and we specify this to be shorter than 2 microseconds, and as you see, this is just about 1 microsecond here, so it works very nice and stable. So now let's go back to our other view, and let's look at the gated setting. This is a little bit more interesting. So you can actually trigger signal pulses using the gated setting as well. So we click that. And as you see, my pulse is a little bit too short at the moment. So I'm actually not generating any pulses. But if we do like that, I get a pulse. And if I shorten this, if I zoom in a little bit, you see that I'm currently generating 1 pulse for each setting. But the special thing with the gated mode is that we can generate a train of pulses or a burst of pulses as long as our signal goes high. The laser will keep generating pulses at a repetition rate set in the graphic the software. So if I change my trigger signal to be a little bit more interesting, there we go. Right now you only see 1 pulse, but what happens here is, if we zoom out a little bit, give you a little bit more light, is that you can see this burst of pulses. My trigger signal goes high and you see a burst of pulses. If I change the repetition rate, of course, you will see that the repetition rate on the oscilloscope of these pulses changes as well. I know it looks a little bit more jittery in terms of the peak-to-peak amplitude, but that's just a matter of the oscilloscope setting in this case. So if I would go back to showing you the pulse, you will still see it's nice and stable. Let's change back so we get a few more pulses. And let's zoom out a little bit more. So we zoom out. And here you see the entire burst in this case. So your signal goes high, you get the laser keeps generating pulses. When the signal goes low, the laser stops. And we can even show you 2 of those bursts. Let's zoom in a little bit. So the last thing to show you now is the signal out. So the signal coming from the laser being detected as each laser pulse hits a pulse monitor in the laser. So let's activate that channel. So this channel now shows you it's supposed to be green, but of course it looks a bit saturated. So this signal, when we don't have an optical pulse, it will be at 1 volt. When we get an optical pulse, it drops to 0 volt for a little while, and then it goes back up. So it's a digital signal. And if we zoom in a little bit on it, you can see it more clearly. So we have the pulse, the digital signal going at 1 volt. We get an optical pulse here, and then it drops to 0 volts for a few microseconds and then goes back, making it very easy for you as a customer to work with it and to synchronize with your other equipment. What I forgot to mention earlier on, we're going to change this back because it's a little bit noisy. It's not noisy, it's just, I prefer to have it externally triggered when I talk about this. So, and there we go. So this pulse monitor counts the optical pulses that are generated by the laser. So it's not counting a trigger signal, it's not counting the internal, it's simply counting each optical pulse as it comes from the laser. And by that, I will hand over the word to Elena.
Thank you,
Elena,
Charlotte.
are you there?
Yes. Very nice live demonstration. Very interesting. So that was Charlotte, our product engineer. And probably as a customer, you might be thinking that, well, it's super nice to have all of these features, but what are the benefits of having them? So let's talk a little bit about that. So having the nanosecond pulses together with the hundreds of microjoules of energy will lead to the very high peak power of the order of more than 125 kilowatts. So the beam quality is great, so it's good. It's m² value is less than 1.3. That means that you can actually focus beam very tightly and reach a very high intensity. That is proportional, of course, to the area of your beam. So the pulse parameters are essential regardless on which operation frequency you run the laser at, and that provides consistency of the operation. As Charlotte just demonstrated, the laser is triggerable from a single pulse up to 1 kilohertz, and that provides a lot of flexibility on the operation. So maybe if you're working with LIBS, you would actually like to go a little bit on a lower repetition rate because your material gets heats up, or perhaps you are more concerned about acquisition time, then you will be going towards the higher frequencies. For example, in LiDAR, usually people prefer to use the laser at a higher frequency, so the acquisition, the data collection goes faster. And of course, by changing the frequency of your laser operation, you can change the overage power. So trigger modes, there are 3 of them. You can choose which one you prefer and which is the most convenient for you to run the laser at. So that gives a lot of flexibility again on the operation of the laser. So the integrated electronics not only provides you with the opportunity to use the laser in internal trigger mode, but also it provides the compact size of the laser head. As you saw, it's quite a small compact laser, and also you can communicate with the laser either using USB or RS-232 communication ports or both. For example, as Charlotte showed, we can monitor the pulses, the pulse repetition rate in the software, but at the same time communicate with the laser with RS-232 communication by sending the commands. So again, that brings a lot of flexibility in your operation. Special cavity design. So due to that, we have a traveling wave and we exclude any special hole burning. And because of that, we have such a good jitter and the pulse stability, which is not typical for the passively Q-switch lasers. So that really differentiates this laser Tor XE from the standard products available. So where this laser can be used, of course, LIBS and a combination of nanosecond pulses together with energy, good beam quality. So that provides a lot of flexibility how much you'd like to focus the beam and which intensity you would like to use, because sometimes perhaps you don't need such a high energy because you will melt your material before you create the plasma. So that can be quite handy. The repetition rate is adjustable. You can choose the rate that you'd like to run your experiment on, and excellent power stability is also an advantage for this application. So speaking about LiDAR, jitters, low jitter is very important in this case because you're actually measuring the time it takes for the pulse to come back. So you'd like to be sure that your pulse is coming on time. And again, adjustable repetition rate brings a lot of flexibility for this particular application, and trigger modes are also helping to implement this laser for LiDAR application. So marking, and here, oh, I forgot to mention, by the way, for LIBS, we have an example here where our laser was used for the aluminum alloys sorting. So the laser was focused and then the spectrum was measured. So that is LIBS application. So here we have marking that was done with our laser, and as an example, so the laser was not focused too tightly, it's only 44 microns, but one can go much more. Its only limit is the diffraction, right? So, and again, for marking, the beam quality, of course, energy, trigger capabilities, big advantages. So laser can also be applied for photoacoustics imaging, and there are also nanosecond pulses with the combination of the high energy, adjustable repetition rate, and trigger capabilities advantages. So with that, I'd like to thank you for participating, and now we are open for the questions. So I'll give a word to Elizabeth, and we are looking forward to discussing it further.
Thanks, Eleanor, and thanks also to Charlotte for a really informative demonstration down there. I hope you've learned something today. I think we can open the floor to questions. We have only 2 minutes left, but Charlotte's going to join us in the lab. Thanks, Charlotte. Have we got any questions there that you...
Actually, we have quite a few questions.
Great.
Which is very nice. Thank you for the interest. And by the way, I've closed the shutters. That's why I'm sitting here without the goggles. So the first 2 questions, I'll group them actually. They're asking about other versions of this laser. Our customer seems to want it at 10 kilohertz and 532 nanometers. Elena, what do we say about that?
So we are working towards getting 532 and of course third harmonic generation such as 355 nanometers, but the repetition rate currently for this unit till up to 1 kilohertz, but we might consider further development. So please send us an email and we take it from there.
Exactly. What do you have more? We have a question if the pulse-to-pulse jitter will change with the repetition rate. And I think I'll answer that. Yes, it will change a little bit with the repetition rate, especially when you just change it. It will be a little bit more jittery, but then it will stabilize to go back to very nice performance. But just when you change it, it will be a little bit more jittery than it is at stable performance. It's a little bit like when you start it up, it needs a few minutes to stabilize.
Thanks, Charlotte.
Elena, we have a question of how is the laser cooled? Does it need water cooling, or is it a heat sink, or how do we do it?
Definitely need a heat sink, so it's a lot of power actually, and we have a heat sink available. It's with the fans or the tech plate that Charlotte demonstrated us in the lab.
But you do not need water cooling, so it's actually in fact air cooled. Yeah. Exactly. Let's see if we can find a few more questions.
Probably got time for one more, Charlotte. So make
Yes,
it the
one
last
more.
question,
We
and then we can round up and let people
is
get back to
the
the lab.
pulse duration or the pulse length variable? We specify that it's 2.5 plus minus 1 nanosecond.
That's actually nice that someone take a look at a data sheet while we were talking. So the pulse duration is fixed per unit, but we have certain variation from one unit to another. But once you get a laser, your pulse duration is stable. It's not gonna change.
Exactly, and you saw that on the oscilloscope that I showed you as well. It's very stable in the peak-to-peak power, you know, the peak-to-peak of the pulses, the amplitude, as well as on the length. You could see it looked like almost only one line there.
Great.
Yeah.
All right. Thanks, Charlotte. I think we'll round it up there. Thanks, Eleanor and Charlotte again. If we didn't answer your question, or you think of another question after we finished here, please email us, sales@hubner-photonics.com. Please also email us and tell us what you think, and hope to see you next time. Bye for today. Bye.
Bye.